Good morning, pre-calculus class. This one is the continuation of chapter 11, so 11.3, geometric sequences. So to look at that, the basic example, so we got 2, 4, 8, 16, 32. So this time, in order to go from one term to the next term, we're not doing addition or subtraction. Instead, we're doing multiplication or division. So as you can see that from 2 to 4, we basically multiply this one by 2. So 2 times 2. So we get 4. 4 times 2, you'll get 8. And then times 2, you'll get 16. 16 times 2, you'll get 32. So now, what does that mean for that 2 right there? So for the value, so the 2. So that means it's a common, well, it's not the common difference anymore. We don't call it the common difference. But instead, we call it the common ratio. So the common ratio. Okay. So anytime they figured out the common number, in order to go from one term to the next term by either multiplying or dividing, it's called a common ratio. So what about the common ratio for this one? 1/2 to negative 1/4. So as you can see that this one is like an alternating sign sequence. So in order to go from 1/2 to negative 1/4, we multiply by negative 1/2. Would that be the same case for the next two terms? Well, negative 1/4 times negative 1/2. Then that would be 1/8. And then 1/8 times negative 1/2, you'll get negative 1 over 16. So for the common difference, the common ratio, excuse me. So this one is negative 1/2. So anytime that you want to find out the number from the first term, from the lower term to the higher term for the geometric sequence, so this one is given as a sub n. So where a sub n is the number in the n term, a sub 1 is the number of the first term, and then odd is the common ratios. Again, n is the number of the term that we want to find out, so n minus 1 for the power. So now let's take a look at that, some of the example we have for the rest of this. So given that a sub 1 is 4, common ratios 3, so you want to find out a sub n. So again, a sub n can be founded by using a sub 1 times the common ratio to the power of n minus 1. So again, if that sequence is considered geometric, so that's the one we need to apply. Well, for those you might be wondering, how do we know that's given as a geometric? Here's the hint. Here's the indicator. It's given with the common ratio, r. Okay? It doesn't really explain that. It doesn't really tells you what kind of sequence this one is, but for the little detail, it actually indicates it. Okay? So make sure that you got to be careful with either r given or d given. Okay, so now let's plug in a number and see what that is. So a sub 1 is 4 times the common ratio, so 3 to the power of n. Well, we don't know what n is because we just want to find out the general formula. Okay, so this one you can say that's the recursive formula for the sequence. So we got a sub n, so that equals 4 times 3 to the power of n minus 1. So for those you might be wondering, can I simplify this a little bit more? Yes, certainly you can, using the properties of exponent. So we got 4 times 3 to the power of n, and then times 3 to the power of negative 1. So as you can see, that 3 to the power of negative 1 is just 1/3. 1/3 times 4, then we do have 4/3. So 4/3 times 3 to the power of n. You can put it this way, or you can just leave it like this, but it's better for you to leave that with the positive exponent. So that's what we got for the structure. And now let's try another one. So the next one we have a sub 1, it's negative 3. Common ratio, it's negative 1. And we want to find out a sub 20. So this time, n is given implicitly. It's 20. So with a sub 1 with the common ratio, again, using the formula, so a sub 20. So we need to find out the number of the 20th term of the geometric sequence. So negative 3 times the common ratio, so negative 1 to the power of 20 minus 1. So it looks like it's an alternating series. So negative 3 times negative 1 to the power of 19. So it's an odd number power. The base is negative. It's negative 1, so that means it still remains as negative 1. So negative 3 times negative 1, so which is 3. Again, so this one is just the alternating geometric series. So just simply multiplying by negative 1 every time. So it's negative 3, 3, negative 3, 3. It just keeps going on forever. Okay, so now let's see what else we have for the next page. So what about finding the sum of the geometric sequence? So let's say that you want to find the sum of the first n term of the geometric sequence. So here's the formula we have. So again, S sub n, that means the sum of the first n term of the geometric sequence. A sub 1, that's what we need to start at first. And then we multiply by common ratios to the power of n. Minus 1, it's the whole quantity right here. So a sub 1 times the quantity of common ratio to the power of n minus 1, and then divided by the quantity of the difference of the common ratio and 1. Okay, so the formula is a little bit kind of complicated for this time, but again, we just need to follow through it. There's a proof. The proof is about using the summation formula. And now let's take a look at that, one of the general example. So plug in a number, a sub 1, common ratio, and then find the sum. So we need to find the sum of the first 5 terms of this geometric sequence. So a sub 1 is 8, common ratio, which is 3, and n is given explicitly, which is 5, so 3 to the power of 5, minus 1, all over the common ratio, minus 1, so 3 minus 1. So what we got here is 8, 3 to the power of 5, so 3 to the power of 3, which is 27, 3 to the power of 4, it's 81, so 81 times 3, then that'll be 243, minus 1, all over 2. So this one, using the operation of PEMDAS, parentheses first, after the exponent, what we got here inside of parentheses, so now parentheses, then that would be 8 over 2, what we can reduce down the number, so then that would be 4. So 4 times 242, so 2 times 2, 42, 4 times 2, 8, 4 times 4, 16, 2 times 4 plus 1, then that would be 968. So the sum of the first 5 terms of this geometric series is 968. It's a big number. Well, because the number is getting bigger and bigger, so you start with 8 and then 24, and then 24 times 3 after that, which is what? 72, and so on. So that's why the number is getting bigger and bigger as you getting close to the 5th term. Okay, so now let's see what else that we have for the rest of this. Okay, so for the next one, okay, let's see. Let me check one thing here real quick, making sure that everything is right. 81. Yeah, that's it. Okay, so the sum. Another one, so we do have n equals 7. A sub 1 is negative 1/2. And the common ratios, it's not given, but we can find it out. So common ratio, in order to go from negative 1/2 to 1, we multiply by the reciprocals. So negative 2. So 1 times negative 2, you'll get negative 2. So that's right, common ratio. So using the sum formula, so S sub n, it's a sub 1 times common ratio to the power of n minus 1 all over r minus 1. So a sub 1 is negative 1/2. Common ratio, negative 2 quantity to the power of 7 minus 1. And then this whole thing, it's all over common ratio, negative 2 minus 1. So got to be careful with the sign change right here. There's so many negative, minuses. So what you need to do, one thing at a time, PEMDAS, exponent inside of parentheses. We started with the exponent first. So negative 2 to the power of 7. Well, negative 2 to the power of 5, then that would be 32. Okay, so negative 2 to the power of 2, then that would be 4. So 4 times negative 32. So negative 32 times 4, then that's, which is negative 128. So that is negative 1/2 times negative 128 minus 1, and it's all over negative 3. So negative 1/2 divided by negative 3, so it's just like negative 1/2 times negative 1/3, so it's positive 1/6. You can do it that way. Negative 128 minus 1, negative 129. Okay, is this divisible by 3? It is. So it looks like it's going to be fractions here. So it's going to be a negative number. So divide it. So divided by 3, top and the bottom. So down the bottom, we got 2. On the top right here, we got negative 43. So it's negative 43 over 2. So just leave that with a fraction. You can convert that to a decimal if you want to. So then that would be negative 21.5. But just keep it like that first. So negative 43 over 2. So now, what about if you deal with the infinite geometric sequence? Infinite, that means the sequence is going to be considered finite. Well, why is it considered finite? Because that, you see that the pattern here? So 1/2, 1/4, 1/8, 1 over 16, 1 over 32, 1 over 64. The number is getting smaller and smaller, and guess what? Eventually, the number is going to be getting close to 0. So this one's kind of like exponential decay function. So remember that the graph for the exponential decay functions. So eventually, so that one, the tail is going to be getting close to 0. Okay, so let me just sketch the graph here properly. So I need the x-axis, y-axis. Again, it's very difficult to draw that with the pen like this. Okay, so here's this x-axis, y-axis template. So for the exponential decay function, so it's going this way. And then it's getting closer and closer to the horizontal asymptote. Eventually, it's getting close to 0. So same thing happened with the infinite geometric sequence. So as you can see that here, the common ratio, it's a very small number. It's 1/2. Compared to what we got for the previous one, the common ratio is either like a big number, integer. But anytime that you see the common ratio, if that's a fractions, so let's say r, it's less than 1. Or you can say that absolute value of r is less than 1. So that means this one would be considered the infinite geometric sequence. Okay, so now let's check it out some of the example here. So the sum of an infinite geometric series, if the absolute value of r is less than 1. So the way to find the sum, instead of using that the complicated structure formula, so we're using the shortcut. It's just a sub 1 divided by the quantity of 1 minus r. Okay, so now let's do that. So let's find a sum for this infinite geometric series. So we got 4, 2, 1. So obviously a sub 1 is 4. Common ratio. So how do I go from one term to the next term? I multiply by 1/2. Because that's 2 over 4, which is 1/2. And then using this information, we're finding out the sum. So S sub n, so that equals a sub 1. So 4 over 1 minus 1/2. So 4 over 1 minus 1/2, that's 1/2. So 4 divided by 1/2 is 4 times 2, which is 8. So the sum of this infinite geometric series, it's 8. Well, as you can see, that is 4 plus 2 plus 1 plus 1/2 plus 1/4, and then plus 1/8, and then plus 1 over 16, so on and so forth. So the number for the first 3 terms is getting smaller, and then for the rest of this, is getting even smaller. So that's why eventually it's going to be getting close to 8. So we got 4 plus 2, 6 plus 1, 7. And then the rest of all the fractions, once you combine them together, it's almost 1. So this one would be saying that's about like 7.9999999. And then eventually it's going to be 8. So now find a sum for 0.9, 0.09, 0.009. So think about this way. So a sub 1 is 0.9. Common ratio. So as you can see that the pattern here, so in order to go from 1 decimal place to 2 decimal places, so we simply multiply the number by 0.1. Okay, so we're moving the decimal point from right to left by 1 decimal place. Again, with all the information that we have, so find the sum. So we got a sub 1, which is 0.9, and then over 1 minus 0.1, so 0.9 divided by 1 minus 0.1, 0.9, so eventually the sum is going to be 1. If you try to add all the decimals together, so we got 0.999999. Keep going, right? So eventually, what is that about? It's 1. Okay, so thank you for watching the video today. So any questions, any comments, so please let me know. Okay, so I'll see you guys next time.